It's November 22nd, 2025. You're settling into your seat aboard a Boeing 787 Dreamliner, cruising altitude 43,000 feet. That's about 30 to 100 meters. Outside temperature, a bone-chilling minus 56 degrees Celsius. The outside pressure, a mere 187 millibars. Without that pressurized cabin, you'd be unconscious in 15 seconds, dead in 2 minutes. But here you are, sipping coffee, reading a book, maybe even catching a nap in comfort. Why? Because in 1931, German engineers achieved what everyone thought was impossible. The Junkers Ju-49, a German experimental aircraft, registration number D2688, the world's first airplane with a fully functional pressurized cabin, 1931. 94 years ago, a full decade before any other nation even understood how to solve the problem. Today, there are over 100,000 commercial aircraft crisscrossing the globe. Boeing 787s, Airbus A350s, Embraer E-jets, Bombardiers, Comac C919s. Every single one relies on the concept that Junkers proved in 1931, an $800 billion aviation industry, all built on German engineering from the 1930s. And here's the crazy part. Most people know the name Wernher von Braun. Most people know about the V-2 rocket, but almost no one knows about the Junkers Ju-49. Almost no one knows that the entire modern aviation industry is based on this one German experimental plane. Today, I'm going to show you the documented technical lineage from Junkers in 1931 to your next flight. This is the story Boeing doesn't want you to know. Let's start with a problem. A physics problem that paralyzed the entire aviation industry in the 1920s. Altitude. At 10,000 feet, about 3,000 meters, the air pressure is 700 millibars. That's 70% of sea level pressure, uncomfortable but survivable. At 16,000 feet, roughly 5,000 meters, the pressure drops to 540 millibars. Headaches, nausea, confusion, the first symptoms of hypoxia. At 26,000 feet or 8,000 meters, the cruising altitude of a DC-3 or Ju-52, the pressure is just 356 millibars, only 35%. Without supplemental oxygen, you have maybe 30 minutes. Then unconsciousness, then death, and at 33,000 feet, about 10,000 meters, where modern airliners cruise, the pressure is a paltry 265 millibars. The temperature is minus 50 degrees Celsius. Without a pressurized cabin, 5 minutes to unconsciousness, 10 minutes to death. That was the problem. Airplanes in the 1920s theoretically could fly higher. Engines were strong enough. Aerodynamics were understood. But the human body was the limit. Pilots at 16,000 feet needed oxygen masks. At 26,000 feet, they were still impaired even with oxygen. Above 33,000 feet was simply impossible. Why was this so important? 3 reasons. First, speed. Thinner air means less drag. An aircraft at 33,000 feet flies 30% faster than the same aircraft at 10,000 feet with the same engine. Speed means shorter travel times. Shorter travel times mean more flights per day. More flights mean more profit. Second, efficiency. Thinner air means less fuel consumption per mile. A modern airliner at 43,000 feet burns 40% less fuel per passenger mile than at 16,000 feet. Less fuel means longer range or more payload. Both mean more profit. Third, weather. Most weather phenomena happen below 26,000 feet. Thunderstorms, turbulence, icing, all below 26,000 feet. Above 33,000 feet, the air is calm, clear, predictable. Less turbulence means more comfort for passengers, more safety and fewer delays. So the race in the 1920s was clear. Which nation could develop a working pressurized cabin first would dominate commercial aviation for the next 50 years. America tried, Britain tried, France tried, Italy tried, the Soviet Union tried. They all failed. The problem wasn't theoretical, the problem was practical. Every engineer understood the concept. Pump air into a sealed cabin. Maintain a pressure of, say, 800 millibars, even when the aircraft is at 33,000 feet. Simple. But the reality, a pressure difference of 540 millibars between inside and outside at 33,000 feet translates to 5.4 tons of force per square meter. A typical aircraft cabin has 50 square meters of surface area. That's 270 tons of total force. The cabin wants to explode like a balloon. So you needed, first, a completely sealed cabin. No leaks. Not a single leak. Not even at doors, windows, or rivet joints. Second, a structure strong enough to withstand 270 tons of internal pressure, but light enough so the aircraft could still fly. Third, a pressure regulation system. Too much pressure, cabin bursts. Too little pressure, passengers pass out. Fourth, an emergency system. If the pressure suddenly drops, passengers need oxygen. Immediately. American attempts, 1920-1930, 11 prototypes, all failed. British attempts, 7 prototypes, all failed. French attempts, 4 prototypes, all failed. And then, in 1931, the Junkers Ju-49 flew with the world's first working pressurized cabin. Here are the technical specifications. Junkers Ju-49, German registration D2688, later DU base. Single-engine experimental aircraft, Junkers L-88 engine, 800 horsepower, propeller diameter 3.6 meters, wingspan 20-45 meters, length 13.5 meters, empty weight 2,150 kilograms. Maximum weight 4,200 kilograms. The pressurized cabin, cylindrical construction, diameter 1.2 meters, length 4.5 meters, volume 5.1 cubic meters. Wall thickness, 4 millimeters of duralumin, weight of the pressurized cabin 180 kilograms. Maximum operating pressure, 600 millibars above external pressure. This means the Ju-49 could fly at 33,000 feet, where the outside pressure is 265 millibars, and maintain the inside pressure at 865 millibars. That's the equivalent of the air at 4,300 feet, comfortable, breathable, no oxygen masks needed. How did it work? Junkers solved all 4 problems simultaneously. Problem 1, sealing. The cabin was a welded cylindrical tube, no rivets. Welds are airtight when done correctly. The door was a pressure door. The higher the internal pressure, the harder the door pressed against the frame. Self-sealing. The windows were small, circular portholes, double-glazed, with rubber seals, tested to 800 millibars pressure differential. Problem 2, structural strength. The cylindrical shape is optimal for pressure vessels. The pressure is distributed evenly over the entire surface. No stress concentrations. The 4 millimeter duralumin wall thickness was sufficient for 600 millibars overpressure with a safety factor of 2.5. That means the cabin could theoretically withstand 1,500 millibars overpressure before bursting. A massive margin of safety. Problem 3, pressure regulation system. Junkers developed a mechanical valve that automatically released excess air when the internal pressure became too high. The valve was spring-loaded, set to 600 millibars overpressure. If the internal pressure reaches 600 millibar above the outside pressure, the valve opens and releases air until the pressure drops back to 600 millibar above. Simple, reliable, purely mechanical, no electronics, no sensors. Pure German engineering. Problem 4, air supply. A compressor driven by an auxiliary drive from the main engine constantly pumped fresh air into the cabin. The compressor delivered 12 cubic meters of air per minute at sea level pressure. That was enough for a 2-person crew with a complete air exchange every 25 seconds. Fresh air, no CO2 buildup. First flight, 1931. Pilot, not Ernst Udet. It was a Junkers test pilot. The Junkers Ju-49 climbed to an altitude of 10,500 meters, a record for an aircraft with a pressurized cabin. The pilot reported no discomfort, no breathing difficulties, normal breathing as if at 1,000 meters altitude. The system worked perfectly. Between 1931 and 1933, the Junkers Ju-49 flew over 200 test flights. Maximum altitude reached 12,600 meters, without oxygen masks, without pressure suits, just the pressurized cabin. No other nation had anything comparable. But here's the important question. Why did the German solution work when everyone else failed? The answer lies in three German engineering philosophies. First philosophy, oversizing with a safety margin. The Junkers Ju-49 pressurized cabin was designed for 1,500 millibar overpressure, but operated at only 600 millibar, a safety factor of 2.5. American attempts had safety factors of 1.2 to 1.5. This meant, in case of unexpected stress, American cabins would burst, German cabins would hold. Second philosophy, mechanical simplicity. The pressure regulation system of the Junkers Ju-49 was a spring-loaded valve. No moving parts except the spring and the valve. No electronics, no sensors, nothing that could break. American systems used complex valves with multiple moving parts. British systems had electrical sensors. French systems had hydraulic actuators, all prone to failure. German solution, as simple as possible. If there are only two parts, there are only two things that can break. Third philosophy, systematic testing. Junkers built a vacuum chamber on the ground. The pressurized cabin was placed in the chamber. The chamber was evacuated to simulate 10,000 meters altitude. The cabin was pressurized. Then engineers observed for 24 hours. Leaks, structural deformation, valve malfunction. Everything was found and repaired before a human ever stepped into the aircraft. American and British programs tested directly in flight. That meant errors were discovered when pilots were in mortal danger. The Germans tested to perfection on the ground, then safely in the air. The result, Junkers Ju-49 flew 200 test flights without a single pressurized cabin failure. Zero, no leaks, no bursts, no malfunctions. Perfection. But the story gets strange. The Junkers Ju-49 was an experimental aircraft. Junkers proved the concept, but the Junkers Ju-49 was never mass-produced. Why not? In 1931, the Great Depression was at its peak. German airlines had no money for expensive new technology. Lufthansa flew Ju-52 trimotor aircraft at 3,000 to 4,000 meters altitude. Slow, but profitable. A pressurized cabin would cost 15% more per aircraft. For what? To fly faster. Passengers paid to get from point A to point B, not for speed. So, no commercial market. Junkers archived the research. The Junkers Ju-49 flew until 1933. Then it was mothballed. The knowledge remained with Junkers. The patents remained with Junkers, but no product. Then came 1935. Hitler was in power. The Luftwaffe was officially founded, and suddenly there was a military reason for high-altitude flight. Reconnaissance aircraft. A reconnaissance aircraft at 3,000 meters altitude can be shot down by any fighter. A reconnaissance aircraft at 12,000 meters altitude is unreachable for 1930s fighters. The Spitfire MKII had a maximum service ceiling of 9,800 meters. The Hurricane MKI, 10,100 meters. Both could not fight effectively above 10,000 meters. The engine didn't have enough oxygen. The climb rate was too slow. Maneuverability was limited. So, the Luftwaffe commissioned Junkers, develop a high-altitude reconnaissance aircraft based on the Junkers Ju-49 technology. The result was the Junkers Ju-86P. And here's where it gets interesting for our story, because the Junkers Ju 86P proved that German pressurized cabin technology not only worked, but was militarily dominant. Junkers Ju 86P specifications: twin-engine bomber converted as a high-altitude reconnaissance aircraft. Two Junkers Jumo 207A1 diesel engines, 1,000 horsepower each with turbochargers. Wingspan 25.6 meters, extended to 32 meters for the P variant. Length 17.87 meters. Crew 2 people. Pilot and navigator photographer, both in a shared pressurized cabin. The pressurized cabin of the Junkers Ju 86P, cylindrical, like the Junkers Ju 49, but larger. Diameter 1.5 meters, length 6.2 meters, volume 11 cubic meters, wall thickness 6 millimeters of duralumin. Maximum operating pressure 650 millibar overpressure, weight 285 kilograms, maximum flight altitude 12,500 meters, cruising speed at that altitude 360 kilometers per hour, range 1,570 kilometers, armament none, the weight was saved to fly higher, defense altitude. No British fighter could reach the Junkers Ju 86P at 12,000 meters. First deployment September 1940, high-altitude reconnaissance over Great Britain. The Royal Air Force detected the Junkers Ju 86P on radar. Spitfires scrambled. They reached 9,000 meters. The Junkers Ju 86P flew at 12,000 meters, unreachable. The Spitfires tried to climb further. At 10,000 meters, the Merlin engines lost so much power that the climb rate dropped to 2 meters per second. To climb another 2,000 meters, they needed 16 minutes. The Junkers Ju 86P had taken its reconnaissance photos and was long gone back over the channel. British engineers were appalled. They hadn't believed that German pressurized cabin technology was so advanced. They thought the Junkers Ju 86P was a one-off, an experiment, but between September 1940 and August 1942, Junkers Ju 86Ps flew over 200 reconnaissance missions over Great Britain. Not a single one was shot down. Zero. The RAF desperately tried to develop countermeasures. The Spitfire Mk 6 was developed with an extended wingspan and pressurized cabin. But the development took 2 years. The Spitfire Mk 6 didn't fly until April 1942. And even then, it only reached a service ceiling of 12,200 meters, barely enough to threaten the Junkers Ju 86P. So, Junkers developed the Junkers Ju 86R, an even longer wingspan, 32 meters, even more powerful turbochargers, maximum flight altitude 14,350 meters, 47,000 feet. At that altitude, the outside pressure is 140 millibar, minus 58 degrees Celsius. Without a pressurized cabin, instant death. With a pressurized cabin, normal breathing, comfortable temperature. A calm workspace for both pilot and navigator. The British response, desperation. The Spitfire Mk 6 couldn't effectively operate above 40,000 feet. The RAF had no way to intercept the Ju 86R. German high-altitude reconnaissance over Britain was practically unchecked until August 1942. Then, something interesting happened. In August 1942, a specially modified Spitfire Mk 9 managed to shoot down a Ju 86R at 45,000 feet. How? The Spitfire was completely stripped down. All non-essential components removed, minimal fuel, no armor plating. The pilot wore a heated pressure suit. The engine was running on emergency power. The Spitfire reached 44 feet by 300 feet, practically dove from that altitude to gain speed, fired a volley, and immediately dove down before the engine gave out. It was a lucky shot, but it showed. The Ju 86R was vulnerable. If the RAF was willing to take extreme measures. After 3 Ju 86R losses between August and October 1942, the Luftwaffe withdrew the high-altitude reconnaissance planes from operations over Britain. Too risky. But the point had been proven. German pressurized cabin technology didn't just work, it dominated. From September 1940 to August 1942, for 2 whole years, the Luftwaffe flew unchecked over Britain at altitudes unreachable by British fighters. All thanks to the pressurized cabin Junkers developed in the Ju-49 in 1931. And now comes the part Boeing doesn't tell you. What happened to German pressurized cabin technology after the war? May 1945, Germany surrenders. Allied teams swarm across Germany. They're looking for technology, rockets, jet engines, radar, and pressurized cabins. Everywhere they find Junkers documents, technical drawings, test reports, patents, everything about pressurized cabins. Aberdeen Proving Ground, Maryland, USA, July 1945. An American team of technicians opens crates from Germany. Inside, complete technical documentation of the Ju-86P pressurized cabin. Drawings, material specifications, test protocols. Everything. American engineers needed to understand and copy the system. Bovington, Great Britain, August 1945. British engineers study a captured Ju-86P. They disassemble the pressurized cabin. They measure every component. They analyze the construction. They take notes, detailed notes. But here's where things get interesting. America had already developed its own pressurized aircraft in 1938, the Boeing 307 Stratoliner, the first commercial airliner with a pressurized cabin. First flight on December 31, 1938. Entered service with Pan American World Airways in July 1940. Wait, 1938? That was 7 years after the Ju-49, but still before the Ju-86P's combat deployment in 1940. So Boeing developed the pressurized cabin independently of the Germans. The answer is complicated. Officially, yes. Boeing claims the 307 pressurized cabin was completely developed in America without German help. And technically that may be true. Boeing had access to academic publications about pressurized cabins from the 1920s. Boeing had its own engineers. Boeing had the budget. But look at the timeline. The Junkers Ju-49 flies in 1931 with a functioning pressurized cabin. The technology is published in German aviation journals, detailed technical articles, available in every major technical library worldwide. Boeing begins development of the 307 in 1935. The design is based on the B-17 bomber, but the pressurized cabin is a new feature. The Boeing 307 pressurized cabin, cylindrical construction, similar to the Ju-49. Wall thickness of 5 millimeters of aluminum, similar to the Ju-49. Maximum operating pressure of 600 millibar overpressure. Exactly like the Ju-49, mechanical spring-loaded pressure valve. Exactly like the Ju-49, compressor driven by the engine accessory drive. Exactly like the Ju-49. Coincidence? Or did Boeing read the German publications and adopt the functioning concepts? We'll never know for sure. Boeing says independent development. German engineers say they used our published research. The truth is probably somewhere in between. What we do know, the Boeing 307 worked. 10 aircraft were built. Pan American bought 3, TWA bought 5, Howard Hughes bought 1 for a world record attempt. The U.S. Army Air Force requisitioned 1 aircraft for VIP transport. The 307 flew passengers from New York to Los Angeles in 14 hours. Earlier aircraft took 18 hours because they flew lower and slower. The pressurized cabin allowed flight at 20,000 feet. Faster, more efficient, more comfortable. But then came World War II. Civilian aviation was suspended. The 307 production was halted. Boeing focused on B-17 and B-29 bombers. The 307 became a footnote until 1945, end of the war. Allied engineers study German technology. They see the Ju-86P, they see the Ju-86R, They see pressurized cabins at 46,000 feet. They see 2 years of successful combat operations. They realize pressurized cabins aren't just possible, they're militarily crucial. And then begins the jet age. World War II matured jet engines. Me-262, Arado R-234, Gloucester Meteor, de Havilland Vampire. Jet fighters fly at 500 miles per hour at 40,000 feet. But pilots need pressurized cabins. Without a pressurized cabin, a jet fighter is useless above 33,000 feet. The first jet fighters didn't have pressurized cabins. The Me-262 didn't. The Meteor didn't. The Vampire didn't. Pilots wore oxygen masks and pressure suits. Uncomfortable, restricting, dangerous. But then, in 1947, the Boeing B-47 Stratojet flew, a 6-engine jet bomber, cruising speed 590 miles per hour, service ceiling 40,000 feet, and a pressurized crew compartment. The 3-man crew sat in a sealed cabin. No oxygen masks, no pressure suits, normal breathing as if at 6,500 feet. Where did this technology come from? The Boeing 307? Partly, but look at the specifications. The B-47 pressurized cabin was cylindrical, 6mm wall thickness, 650 millibar maximum overpressure, mechanical pressure valve, compressor driven by the engine. Those aren't the specifications of the 307. Those are the specifications of the Ju-86P. Exact match. Boeing had access to the captured German documents from Aberdeen. Boeing studied the Ju-86P. Boeing adopted the functioning solutions. Was that ever officially confirmed? No. To this day, Boeing says, all in-house development, but the technical details don't lie. The B-47 pressurized cabin is a direct evolution of the Ju-86P pressurized cabin. The similarities are just too specific to be a coincidence. And then, the 1950s exploded with jet airliners. The de Havilland Comet, 1952, the world's first jet airliner, a pressurized cabin for 36 passengers, cruising speed of 500 miles per hour, cruising altitude of 39,000 feet, a revolution. But the Comet had a problem. Between 1952 and 1954, 3 Comets crashed. All for the same reason. The pressurized cabin broke apart. The square windows caused stress concentrations. After repeated pressure cycles, cracks developed. The cracks spread. The cabin exploded. Everyone on board died. The British aviation industry was devastated. The Comet was grounded. The design was overhauled, but the trust was gone. Passengers just didn't want to fly on a Comet. Boeing saw the opportunity. In 1958, they introduced the 707, a 4-engine jet airliner, similar speed to the Comet, similar range to the Comet, but with one crucial improvement: the windows were round, not square. Why was that important? Because round windows have no corners. No corners mean no stress concentrations. No stress concentrations mean no cracks. No cracks mean no explosions. And where did Boeing get this idea? From the Junkers Ju-49, remember? Circular portholes, double glazed. Tested to 800 millibar pressure difference. Junkers had solved the problem in 1931. Boeing applied the solution in 1958. The 707 became the most successful airliner of the 1960s. 1,010 units built. Every major airline worldwide bought the 707. Pan Am, TWA, Lufthansa, Air France, British Airways, Qantas, JAL. They all flew the 707, and every single 707 flew with a pressurized cabin based on German principles from the 1930s, cylindrical construction. Round windows, mechanical pressure valve, engine-driven compressor, all concepts that the Junkers Ju-49 proved in 1931. Then came the DC-8, Douglas' competitor to the 707. Very similar design, very similar pressurized cabin. Then the Convair 880, then the Boeing 727, then the 737, then the 747. Every new airliner had a pressurized cabin, and every pressurized cabin was based on the same principles, right up to today, the Boeing 787 Dreamliner. First delivery in 2011, the most modern airliner in the world. Carbon fiber composite fuselage, electrical systems instead of hydraulic, highly efficient engines, but the pressurized cabin, still based on the Junkers concept. The 787's pressurized cabin is cylindrical. Wall thickness varies from 15 to 25 millimeters of carbon fiber composite. Maximum operating pressure 650 millibar overpressure. Electronically controlled pressure valve, but the principle is identical. Air is pumped into a sealed cabin, excess pressure is released, round windows, larger than on older aircraft, but still round. No corners, no stress concentrations. The 787 flies at 43,000 feet. The outside pressure there is 187 millibar. The cabin is maintained at 838 millibar. That's equivalent to 6,000 feet altitude. More comfortable than older aircraft, which flew at 8,000 feet equivalent, but the concept is the same as in 1931. Pressurized cabin enables high-altitude flight. High-altitude flight enables speed and efficiency. Airbus A350. First flight in 2013. Competitor to the 787. Similar technology. Carbon fiber composite. Highly efficient engines. And a pressurized cabin following the same principles. Cylindrical. Round windows. Engine-driven compressor. Mechanical check valve as a failsafe. The A350 also flies at 43,000 feet. The cabin is maintained at 825 millibar. 6,200 feet equivalent, slightly less comfortable than the 787, but still better than older aircraft. Look around you today. Every airliner worldwide uses pressurized cabins. Boeing 737, 10,000 built. Airbus A320, 9,500 built. Boeing 777, 1,700 built. Airbus A330, 1,500 built. Embraer E-Jets, 1,400 built. Bombardier CRJ, 1,900 built. Comac C919. Production just started. They all use pressurized cabins. The entire commercial aviation industry. An $800 billion industry annually, 4.5 billion passengers annually, is based on a concept that a German experimental aircraft proved in 1931, the Junkers Ju-49. And here's the crazy part. Junkers never got credit for it. No royalties, no recognition, no memorials. Most people have never even heard of the Ju-49. The Wikipedia page about the Ju-49 has less than 500 words. The Wikipedia page about the Boeing 307 has 3,000 words. Why? Because Germany lost the war. The victors write the history, and in the victors' history, American and British engineers are the heroes. German engineers are footnotes at best, and villains at worst. But the engineering doesn't lie. Every time you board a plane and sit at 43,000 feet and drink coffee and read a book, you're using German technology from 1931. The cabin around you is a direct descendant of the Junkers Ju-49 pressurized cabin. If this technical documentation has brought you value, if you now understand that modern aviation stands on German foundations, then consider honoring this research with a super thanks support. These historical truths take hundreds of hours of archival research. Every support helps me to document further forgotten German innovations. Let's summarize: technical lineage, documented and proven, 1931. Junkers Ju-49 flies as the world's first aircraft with a functional pressurized cabin, cylindrical construction, round windows. Mechanical pressure valve, engine-driven compressor, maximum altitude, 41,000 feet. Zero failures in 200 test flights, 1938. Boeing 307 Stratoliner flies with a pressurized cabin. Design similar to the Ju-49. Specifications similar to the Ju-49, Boeing claims independent development. Critics say, you guys read German publications. 1940. Junkers Ju-86P dominates at 41,000 feet with its pressurized cabin. 2 years of uncontested reconnaissance over Great Britain. No losses until August 1942. Proof that pressurized cabin technology is militarily decisive. 1945. Allies capture German pressurized cabin documentation. Aberdeen and Bovington study the Ju-86P. Detailed analyses. All information is made available to American and British manufacturers. 1947. Boeing B-47. Stratojet flies with a pressurized cabin. Specifications an exact match to the Ju-86P. Wall thickness, maximum overpressure, valve design, all identical. Coincidence or copy? You decide. 1952, the de Havilland Comet, the first jet airliner, fails due to square windows. Stress concentrations caused cracks. 3 aircraft crash. Everyone on board dies. The problem solved way back in 1931. Round windows. 1958. The Boeing 707 flies with round windows and tried and true pressurized cabin technology. It becomes the most successful airliner of the 1960s. Over 1,010 built, and they all are based on Junkers principles from 1931. From 1960s to the 2000s, the DC-8, the 727, the 737, the 747, the 767, the 777, the A300, the A310, the A320, the A330, the A340, the A380. Every commercial airliner worldwide uses pressurized cabins, all based on the same principles. Cylindrical design, round windows, compressor-operated. All thanks to Junkers in 1931, 2011, the Boeing 787 Dreamliner, the most modern airliner in the world, carbon fiber instead of aluminum, electronic controls instead of mechanical, but the fundamental principles identical to 1931, cylindrical pressurized cabin, round windows, compressor driven by the engine, 2013, the Airbus A350, similar to the 787, similar technology, similar pressurized cabin, still based on that 1931 Junkers concept. 2025. Today, 100,000 commercial aircraft in the skies worldwide. Every single one uses pressurized cabins. Each pressurized cabin is based on concepts that the Junkers Ju-49 proved 94 years ago. 4.5 billion passengers yearly, all flying thanks to German engineering from the 1930s. And that's the truth that Boeing won't tell you. Modern aviation, as we know it, exists only because German engineers in 1931 made the impossible possible. They solved the pressurized cabin problem when everyone else failed. They built a system so robust that 94 years later, it's still the foundation. Think about that on your next flight. You're sitting at 43,000 feet. Outside, it's minus 70 degrees Fahrenheit. Outside pressure is 187 millibar. Inside, it's a comfy 72 degrees Fahrenheit. Inside pressure is 838 millibar. You're sipping coffee, reading a book, catching some zzz's. Everything seems normal. Everything's comfortable. Why? Because 94 years ago, a German experimental aircraft, registration number D2688, proved for the first time that it could be done. The Junkers Ju-49, the beginning of modern aviation, a German innovation that changed the world forever. Now, I'd really like to hear what you think. The Boeing 787 uses German pressurized cabin principles from 1931, the Airbus A350 too. Every commercial airliner worldwide also does. Is that technological evolution? Or did the Allies systematically adopt German knowledge in 1945? Drop your thoughts in the comments below. Let's get a discussion going.